Right, there's an introduction. And so this is talking through engineering physics. You can see, if you read the introduction, that this engineering physics is basically, like I said, linking a generation of heat, thermodynamics, and causing things to rotate, heat engines. And a rotating heat engine can then be used to do useful work, moving cars about, moving machinery about. I mean, the steam engine is a heat engine. The jet engine is a heat engine, and the internal combustion engine is a heat engine. You can move stuff about with a heat engine and get it to do useful work. So you can get it to rotate a mill, and that's how they used steam engines in the mills at the beginning of the Industrial Revolution and so on. So heat engines are, heat engines are used to generate electricity as well. I mean, every electricity generating plant really is, it's a heat engine, almost all of them. Solar panels, which are photovoltaic and not. But most electricity generating is basically a big kettle. So you find a form of heating water, whether it's with concentrated sunlight using mirrors or nuclear power, and you get it to boil water, which turns a turbine, which turns a generator, which generates electricity. Well, boiling the water and getting it to turn a turbine, that's a heat engine. And so basically most power generation is from heat engines. And so they are ubiquitous amongst engineering forms of energy that you can use to then do everything else that you want to do. And it's kind of basic physics that underlines virtually the entire of industry. So it's quite important. So this is where we come from. So, and a heat engine nearly always goes round. They don't always go round. They reciprocate. But reciprocating engines, things that go backwards and forwards, they nearly always end up causing something to go round. So the treadle on an old-fashioned sewing machine and pedals on a bicycle. That's a reciprocating motion going backwards and forwards, but it also makes a crank go round, and that is an engine. If you drive the crank round using heat, then that's a heat engine. And this is the basics of lots and lots of machinery. And so what we've got to do is to link the heating bit with the engine bit, the rotary bit, the bit that goes round. And that's what this engineering option topic is all about. So you can see that they talk about the thermodynamics section, breaking down the first law of thermodynamics, which I'll go through, heat engines and efficiency. Refrigerators and heat pumps, those are reverse heat engines. So that is making things go round and using it to move heat. And that is the opposite of a heat engine. But they are, of course, linked. I mean, it basically does the opposite thing. Refrigerators and heat pumps are also very useful devices. And so they are, basically their structure is the same as a heat engine. It just works in reverse. It's a bit like the difference between a dynamo and an electric motor, or a alternator and electric motor, a generator and electric motor. They do the opposite. So one converts one sort of energy to the other, and the other one works it back. Okay, so we've got heat engines, and then they talk about the various different issues that are associated with the second law of thermodynamics. So the second law of thermodynamics is it's about something called entropy, which we'll cover when we get to that bit. Entropy is it's a measure of the disorder of a system, and the universe has a tendency to increase the disorder of a system without requiring any input to do that. And so that happens naturally. That's the general way that things move. So increasing the randomness, increasing the disorder, that's increasing entropy, and that is the second law of thermodynamics. And you have to put energy in to stop that happening in order to create order, and so on. Right, so so that is basically what the engineering option is about. And so we start with then this rotational dynamics, and now you've already seen the links between linear and rotary motion. So I want you to start spotting those links as we go through this in the right order. And we've got the concept of the moment of inertia, which I have already mentioned. So I is the moment of inertia. It's equivalent to mass, but it's for rotary motion, and it is the sum of m times r squared. If you've got just blobs of mass that are a distance r from the axis of rotation. If you've got different shapes, then you have to use those formulae, and they have to give them to you because you're not expected to remember them all. So this is the moment of inertia, okay, and it says I depends on both the total mass and how the mass is distributed. Okay, so for example, a rod pivoted in the centre has a different moment of inertia from that which it would have if it was pivoted near one end. In other words, if you've got a rod and you pivot it here and it rotates, that has a different moment of inertia to the same rod pivoted there, and that rotates. Ooh. Okay, can you see that the distance of the mass from the centre of rotation here is more r is bigger, okay, which means that I will be bigger. Okay, it's the same mass, right? So and r here is smaller, relative distance from the centre of rotation. I mean, effectively, you've got a bit there and you've got a bit there, haven't you? But here it's there, and so and that distance is twice this distance. Yeah. Okay. So so I will be bigger in this second situation. If oh, that's a bit confusing. I'll get rid of that dot because it looks like I'm rotating it around there. Woo! Didn't need to do that. Oh. Okay. Right, so so those are that's the moment of inertia bit. Right, so then if we read what it says next, it says that the specification does not require students to be able to derive expressions for moment of inertia, because that requires differentiation, integration, and so you're not expected to be able to do it, not for A-level physics. So they have to give them to you, okay, so but they may be required simply to add moments of inertia. So for example, they would be expected to know that if a small mass is added at a radius r to a wheel of moment inertia I, the new moment is I plus mr squared. So it's just a smaller mass added, okay, so you just add them, okay. So that is the moment of inertia. And then there is this idea of rotational kinetic energy. So rotational kinetic energy is exactly the same as linear kinetic energy, except it's I omega squared, or half I omega squared, rather than a half mv squared. And of course, omega is measured in radians per second, okay? It says that the total kinetic energy of an object rotating about an axis can be found by summing the kinetic energies of all of the individual particles. So if you've got two masses that are a distance from the centre of the rotation, and the thing's spinning, like, I don't know, a spaceship spinning, and you've got a virtually mass-free rod, and then there's two habitation things, and they're right. Can you see that the kinetic energy of the whole thing is going to be a half I omega squared. And of course, I is the mass of this times that r squared, and the mass of this times that r squared added together, which is this bit. And you've got to then multiply it by omega squared in order to get the kinetic energy. So this is a spaceship. Why would you want to rotate a spaceship? So that you can simulate gravity, so you don't get your bones depleted of calcium. So yeah, it would be spinning like that, and then the people would be standing up like that and like that. Yeah, it would be really quite unpleasant to be in there, I think. It's like a centrifuge. Okay. Maybe if it was very big, it would be all right. Yeah, you'd end up with a spinning thing, skies out of the windows, if you had any windows. Anyway, interesting thoughts. In fact, this is one of the problems of, I mean, I personally think this is the difficulty with this option topic. So the option topics are designed to be as difficult as each other. This option topic, I personally think, is possibly the easiest. It doesn't include any logarithms. It doesn't include masses of stuff that you have to remember exactly. The difficulty is the actual questions, because they have to illustrate the system. And of course, rotating systems require three-dimensional illustrations, really. And so quite often the example questions that you get for this, they show the same system from two different points of view. So you can see how three-dimensionally the system is put together. And they have to describe how the thing is spinning quite often. And also how they're going to change the spin in order to ask you a question about it. And so interpretation of the diagrams for and the descriptions of the situations, that is the hard bit of the questions on the engineering physics option paper. So so the actual questions are really quite difficult to get your head around. So they nearly always have almost a page of description and diagrams, and you've got to interpret that, and that requires a certain amount of time. And I think that's the hardest bit of this. The actual physics really quite straightforward, especially if you've got your head around linear mechanics. Okay, so there is an object, and it has kinetic energy, but it's rotational kinetic energy because it's spinning. Okay, right. And it's because things that are spinning have energy that they don't talk about things rolling down ramps very much. They talk about frictionless ramps and blocks sliding down instead. If you have a can of beans and you roll it down a ramp, it behaves very differently to a block with tiny little almost massless wheels rolling down the ramp. Yeah, because of this rotational kinetic energy. So the energy of a moving object includes the rotational energy. So if you have your gravitational potential energy at the top of your ramp, and you want to do the gravitational potential is equal to kinetic energy at the bottom of the ramp, then it only works if you don't rotate anything. And so, yeah, rotating your can of beans means that the linear kinetic energy of your can of beans is not going to be the same at the bottom of the ramp. So you've got to be careful when you're creating physics questions that you don't introduce added complications, because you're making things spin. So it's never a ball that rolls down a ramp. It never is. I don't know if you've noticed. Anyway, okay. Right, so now the next thing then, let me clear my drawings. The next thing then is flywheels. So because you can store, well, you can, right, kinetic energy of rotating systems means that you can store energy that way. And that's what flywheels do. So a flywheel is an object that is made to rotate, and if there's lots of mass at the outer rim of the thing that's rotating, you can store lots of energy that way. And so a flywheel can do all sorts of things. So, and I've pulled up one or two things about flywheels. Okay, so here are some examples of flywheels. All of these metal ones are flywheels in engines, normal engines. Can you see it's there? The flywheel is between the engine and the gearbox, and that's because the engine makes the flywheel spin, and but the engine is not necessarily going at the same speed as the wheels, and so you've got a gearbox, which means that you can change the ratios, and what you do is you have a flywheel in there that keeps rotating. It's got a moment of inertia and lots of kinetic energy, and so you can smooth out the motion that the power, which is from a reciprocating engine, actually nearly always delivers. So flywheels can smooth out power, and they can keep things going when actually there's no power being delivered. Okay, so you don't get power delivered 100% of the time with most heat engines. Got pistons going backwards and forwards, and there's one power stroke, and sometimes there's only two strokes. But sometimes, I mean, most car engines are 4-stroke engines, so there's one power stroke and 3 non-power strokes. It's suck, squeeze, bang, blow. So suck is the induction, so that's where the fuel air mixture comes in. Then there's squeeze, which is a compression stroke where the fuel air mixture is compressed. And then there's bang, which is the power stroke where the ignition causes the fuel air mixture to burn very rapidly, and that causes the piston to be forced out. Now that's the power stroke. And then blow is where the piston comes back up and it pushes the exhausted gases out of the exhaust valve. And that is a 4-stroke engine, but you can see there's one power stroke for 4 movements of the piston. And so the power delivery from a 4-stroke engine is really lumpy, and flywheels can smooth that delivery. So you store energy in a flywheel. Now, some flywheels, and certainly in these old steam engines, can you see this one? This one's lovely. That's quite a big flywheel. Okay, and it rotates and it can store energy. Okay, and so even though you might have just a single cylinder producing power, the flywheel keeps the thing moving in between those power strokes, so you get reasonable power delivery to the wheels, which is lovely. So all of these are flywheels in regular engines. Okay, and this one is obviously a steam engine with a chimney. So I want to show you some video of flywheels actually in use. So excuse me. So this is the flywheel, and you can see that it's attached via a belt to whatever this steam engine is powering usually. And in this case it looks like it's a combine harvester or a thresher or something. Turn that one down a minute. Okay, so please don't confuse it with the wheels that actually go round on the ground. Obviously this is a stationary engine. In other words, well, it's an old-fashioned steam engine, obviously used for farming, and the engine can be used either to drive the wheels, which makes that traction engine move, Or you can see that it runs this flywheel, which then has a pulley system which can be used to make other bits of equipment rotate. And you can take the energy from the engine and use it to run other equipment. And this is how a lot of industrial engines were used initially. So you can use a stationary engine to run a water pump in a mine, or a threshing machine like this one on a farm. But a traction engine means if this engine's got wheels, you can take it from one farm to another farm. And yeah, this was how the Industrial Revolution was born, really. Okay, so there's a flywheel, and yeah, no, I'm not going to do that one. Right, let's pause that. I've got this is a high-speed flywheel. I want to show you one spinning up. One of the things that you can use a flywheel for is storing energy, which means that then when you're no longer powering the flywheel, the energy is still there, and you can use that energy to do whatever you want with. So you just have to have some way of getting the energy back out. And this particular arrangement has got, can you see here, this is, oh, need a pen. This is an electric motor. There are two green gears. There's a little green gear and there's a big green gear. So the electric motor turns the little green gear, which then turns the big green gear, which then turns the flywheel. And this thing is a flywheel. So that goes round really fast and spins. And then you can disengage the electric motor and the flywheel keeps spinning. And then you can switch it so that the flywheel rotates the electric motor and uses it as a generator. So then you can get the energy back out, and it will show you in just a second. It will show you the motor no longer being powered, but energy coming back out of the flywheel and lighting a series of lights. So let's show you this working. So that's going at maximum speed, and there are the lights that it's lighting. So so at the moment the electric motor is just driving that, and then you switch it over and use the motor as a generator, and the flywheel then has stored that energy and it's returned as electricity. So I just thought this was a really neat demonstration of the energy stored in a flywheel then being used to generate electricity. And in fact, this is how regenerative braking works on electric vehicles and stuff, so that you can reclaim the energy. Obviously, it's not used to generate light, it's used to push charge back into the battery. Okay, so that's that one. And I've got one more way that the flywheel can be used to return energy. So this is a lovely little 3D printed flywheel car. So this thing is the flywheel, and it goes round and round. Okay, and you spin it up by putting the car down on the ground and moving it along, and then picking it up and moving it along and picking it up and moving it along. And every time you do that, you spin this flywheel faster. And then when you put the car down, the flywheel with this series of gears can turn the wheel and power the vehicle along, it's absolutely lovely. Okay, let's clear those and let's make it larger, and I can show it working. Okay. So that's spinning up the flywheel. Woo! And off it goes. And there. Okay. Put some rubber wheels on. Just elastic bands. Amazing what a bit of friction will do. Woohoo! Okay, so the flywheel keeps it going, and returns. And this is a really steep one. Woohoo! Woo! And even steeper. It's very cool. Right, okay, that'll do. Okay, so yeah, flywheels can store energy, and some of them are little, like in this little electric flywheel car, toy car, and some of them are absolutely massive. There are some very, very large two-stroke engines powering, or four-stroke engines powering big ships. And they have absolutely enormous flywheels because they're not really limited by mass the same way that most vehicles are. And so they can have really big flywheels. And there's an advantage to having a big flywheel that's spinning in a boat. And that is that flywheels also have this gyroscopic effect. They don't want to rotate the axis of rotation. If you force the axis of rotation to move, then it kind of pushes back on you and makes you spin the other way. What that means is that a big flywheel spinning in a ship will stabilize the ship, the motion of the ship. And when you're on waves, big waves at sea, especially if you're in the military and you want to fire big guns, pointing a big gun in a big sea is a bit hit and miss, literally. But if you've got a big flywheel that you can use to stabilize your boat, then you have an advantage. So big flywheels are quite often used on boats. Especially military boats, and of course it helps with seasickness as well. Okay, so flywheels, right? Let's go back to our list of things. Okay, so if we look at what it says about flywheels, there's the push and go toy car, which we've just seen. Experimental vehicles that use flywheel batteries. So the flywheel is charged up by an electric motor at a fixed location, and then you can drive the car until the flywheel doesn't go around anymore to the next location. Well, yeah, no, I don't think there's very many of these cars anywhere, but that it's certainly a thought, and it would work up to a point. You just need lots of locations to spin up your flywheel again, and regenerative braking in systems. I don't know of regenerative braking systems that are called KERS. This specification was written 20 years ago, really. Although this particular specification was started in 2016 for first examination in 2017, they've been doing engineering option for many years. And the kinetic energy recovery systems, they're not really called that. They're regenerative braking, that's what people call them now. Okay, in other machines, flywheels even out fluctuations in rotational speed that will occur if the flywheel were not fitted. So the flywheel is fitted to the crankshaft. Right now, the crankshaft is a part of a rotating engine, and it's the bit that goes round. If you think about the pedals on a bicycle, let me pull up. Okay, so this is there is the pedal. Okay, this bit, that's the crank. In fact, this really is a connecting rod. The crank is the bit in the middle. So this arrangement goes round, obviously, and you can see that there's a gear wheel which is attached to a chain, which then drives the back wheel. But this is a crank. So now, on a bicycle, obviously, the crank is being driven round by your legs, your feet. They go round. So you put your weight on one, then you put your weight on the other, and then you put your weight on one, and you time it right so that you get the crank to go round always in the same direction. But in a car engine, the same thing happens. It's just that the pedals of the pistons, effectively, and the power stroke of the piston engine drives the crank round. So in a car, instead of just having two, you would have four usually, one for each piston, and they're connected together by a crank shaft which rotates round, and it's got a peculiar shape. So this is the crankshaft. So this is what they look like. Okay, so this is a crankshaft, and you can see that they're all really polished because there are connecting rods which go round. Okay, so here is the connecting rods attached to the crank. This one's got two crank rods, I think. Yeah, it's two crank rods, and this is one there. That's better. Okay, so this is, I mean, obviously the cylinders are not there, but this is the pistons, 1, 2, 3, 4. This is the connecting rod for each of the pistons, or the con rod. Then there is, these are the crank bearings in their various positions. And the silver bit, that is the crank, okay? And you can see that although it's got like kind of gaps in it, this thing, it rotates around that axis of rotation. So this is the crank, and attached to the crank at one end will be the flywheel. So that is that's how an engine is constructed, and so the pistons push down, and they and the crank effectively turns that linear motion, which applies a torque, into rotary motion to make the thing go round. And you can see that it's really lumpy, right? So each of those is going to give you one power stroke for 4 strokes. So the crank goes round, and you go up and you go down, once up, once down for each rotation of the crank. So you get, for each piston, you get 1 power stroke every 2 rotations. So effectively, because there are 4 pistons, you get 2 power strokes per rotation. Okay, so 2 of those pistons will be pushing it, and they push at different times. So the timing of an engine is really important. So now, if you've not got 4 cylinders, if you've only got 3 or 2 or only 1, some motorbike engines are a single cylinder, then you only get a power stroke every other rotation, which means that you've got to keep the engine going round. Because if you haven't got anything to keep the engine going round, it won't keep going round the same way. So you've got, the flywheel there stores some of the energy. It smooths out power delivery. It makes the thing bearable to drive. Right, okay. So there's this idea then of a crank. Let's go back to our thing. Which evens out. Can you see there in bold? It's obviously very important. It's probably going to come up in your exam. Evening out the rotation speed, the fluctuations caused by the fact that your power is not being delivered smoothly. It's not like that electric motor at all. Okay, so heat engines do not deliver power smoothly. Right, not mostly, they don't. Some heat engines do. Jet engines are quite good. Anyway, right, okay. So an internal. So this is a flywheel is fitted to the crankshaft. So that's that ziggy zaggy shaft. That's the crankshaft of an internal combustion engine or a reciprocating steam engine. Reciprocating just means going backwards and forwards. So again, it's a piston engine, where the load torque may be fairly consistent, but the torque provided by the engine varies with the pressure in the piston and the crank angle. The flywheel also takes the engine over the dead centres. So if you've got a position where, for for example, the pedals of your bicycle are exactly up and down, right? You can jump on the pedals and it won't push it to the left or the right, will it? Because it's in a dead center, right? So all of the force is going exactly through the axis of rotation, which means that there's no torque. Even if you apply lots and lots of force, that's a dead center. And lots of engines have dead centers, especially single cylinder engines. And so you want to be able to push it over the dead center so that it keeps rotating. And that is what one of the things that a crankshaft does. So that this is smoothing out the power delivery of the crankshaft. Okay, so the flywheel also takes the engine over the dead centers, positions at the top and the bottom of the piston stroke, at which the crank and the connecting rod are in line and there is no turning effect. Okay, in such engines, most of the time the load torque and the engine torque are different. So when the engine torque is greater than the load torque, the flywheel accelerates and vice versa. Okay, the flywheel accumulates energy as it speeds up and gives up the energy when the load torque falls. Okay. Right. It says the greater the moment of inertia, the smaller the fluctuation in speed. So it's like having more mass. It makes it easier to keep the thing going. So, and this is now comparison of different flywheels. And there are quite a few questions which are on flywheel design and what the best design is for a particular function of a flywheel. And so when you are answering questions like this, you need to mention how far away from the axis of rotation the mass is and what the moment of inertia is and how you could change the moment of inertia to increase the distribution of the mass to increase the moment of inertia. And how that would mean that you could store more energy. And so that there are quite a lot of questions like this. So you shouldn't think that flywheels are not important. They are very likely to come up. Okay, so it says flywheels fitted to large Victorian steam engines, such as those used in pumping stations and textile mills, have massive rim fitted with spokes. So there is a massive rim fitted with spokes. This gave a greater moment of inertia than if the same mass had been used to make a solid disc flywheel of the same diameter. Okay, so this has got a lower moment of inertia than this one, even though there's the same amount of material present. I know, it's cool, isn't it? So, so then they talk about factors affecting storage of energy for a flywheel. And so you need to be aware that there are differences because of the distribution of the mass. And then there's flywheel batteries. So that is using then an electric motor as a generator. And then we've got machine tools. So machine tools are things for punching holes in or punching shapes out of bits of metal or something. And quite often you need, sort of a big force for a short time. And a flywheel is a way of doing that. So you can spin up a flywheel and then you can use that energy to go kerthunk. And you've punched out another load of holes in this metal plate, for example. So they can be driven hydraulically or pneumatically, but some utilize an electric motor and a flywheel. The flywheel is brought up to speed and then supplies the energy for the punching or pressing operation that happens momentarily. If a motor on its own were used, it would simply stall. So, that this sort of thing, this is where the description of what's going on can be quite complicated, okay. Right now, I'm inclined to kind of skip this bit. These are the Suvat equations. Okay, they are exactly the same. You just have to remember that the angular speed and the angles must all be measured in radians per second or radians. And so if you are given speeds in revolutions per minute or revolutions per second, you've got to convert. So let me just remind you how to do that. So if you've been given, I don't know, 250 revolutions per minute, okay, so that's not particularly quick. The idling speed for a big car engine might be 700 revolutions per minute. So that's totally normal. 1,000 revolutions per minute maybe, and it might go up as far as, well, if it's a highly tuned motorbike engine, it might go up to 7,000 or 8,000 revolutions per minute. So 250 is not that. That's a really low tune engine. So we're going chug, 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 chug. Right? Okay. But let's imagine that this is the speed, and we want the angular speed. We want omega. So they've given you omega, but it's in revolutions per minute. So we've got to change the units. We need it in rads per second. That's what we need. This is the SI unit. So what we're going to do is we are going to take our 250 revolutions, and one revolution is 2 pi radians. So now we've got the revolutions per minute in radians per minute. Okay, now we want radians per second, so we have to divide by the number of seconds in a minute, which is 60. So now this is omega, and it is in rads per second. Okay, so let's just do it. So 250 times 2 times pi divided by 60 equals, okay, and we end up with 26.2 rads per second. Okay, you can leave it as some number of pi. I mean, on my calculator it came up as 25/3 pi rads per second, but yeah, you might be penalised, especially if they ask you to give the correct number of significant figures. So I would go with this one, even though you're tempted to do this one. You can use this one if you want to use it later in a question, okay? But yeah, use this routinely. Okay, right, let me clear my drawings. I'm going to stop sharing a minute. Okay, so now the next thing that I want to show you then is this torque and angular acceleration section. So now moments is something that you already know, and a torque is basically a moment. So this is T for torque, okay, and of course it's the force times the perpendicular distance from the pivot. So you can see in this arrangement we've got a mass which is on a bit of string, which is wrapped around an axle, and this thing is a flywheel. So if you were to look at it from over here, it would look like this, with the string falling down one side. There's the mass, and then behind it, the flywheel. Okay, so that's what it would look like. And you can see that the torque that the mass is applying is going to be the distance between the center of rotation and where it's applying. So if we were to draw our dotted lines up like that, okay, that is R, that distance there. And so then our torque then would be the mass, which is the weight of the mass, I suppose I should say. Let's do W times R, which of course is mgr. So that is going to be our torque, and that will cause this flywheel arrangement to turn. Right now, the rate at which it will turn will speed up, okay, and it's going to be like F equals ma, except that instead of F equals ma, we're going to use T, the torque it causes, this mass, it's not the mass, it's the moment of inertia, get it right, times the angular acceleration. So here is my torque that I've just worked out, and I can, if I know my moment of inertia, I can work out my angular acceleration, and then I can use suvat, but it's the angular version, to work out what my, for example, final velocity is when the mass reaches the end of the string, falls off or something, I don't know. So this sort of arrangement, can you see that I ended up drawing a second picture in order for you to be able to interpret this figure? And and this happens a lot. I mean, right, let me clear my drawings. I'm going to show you one or two diagrams from examples. So here is a picture of a satellite, and instead of being a plan view or a two-dimensional view, they've given you a three-dimensional view so that you can see how this object is going to rotate. Okay, and they've given you description, and they've told you about the masses of the various bits, and they've labeled all the parts, and they've drawn the little circle with the arrow on to show you that which bits it's spinning, and they've drawn in the axis of rotation, and they've given you the distances. Can you see how complicated this is? This is just one example of a question, and there are so many like this. The next question. There is a diagram with a load, and can you see the axis of rotation again is labeled with distances and stuff? Okay, let's look at the next question. This one's got no picture. That's quite rare. Okay, let's find another one. Oh, look, more than one picture showing how the solar panels move out and how that's going to change the this shape of this device that's rotating, and you've got the axis of rotation, and they've given you the direction and the curly arrow that shows you that it's rotating about that axis, and so on. There is another diagram. Okay, this is looks like a dynamo torch, yeah. So you move the handle, and it causes the flywheel. Look, it's got a little flywheel in there, and so on, and long descriptions about what happens as well. This is the hardest bit, I think, of these sorts of questions. That's one lot of questions. Here's another one. This is a salad spinner, and you've got gear wheels causing things to rotate, and you've got more than one. So this is a plan view, and this is a side view, and this is a salad spinner. Okay, there is it's a drop leaf table. Okay, and when the leaf falls, oh look, coffee cup spills, and so on. There are diagrams. Oh, that's that same question. There is a spinner for a garden sprinkler. Okay, can you see? Again, they've given you two images. One's a plan view and one's a side view, so that you can see how the different parts go together, because they have to give you the three-dimensional picture for your head. So diagrams, right, there's a diagram of a washing machine. So you've got a motor and a driving belt, and then this is the washing inside the drum, and so the drum spins, and so on. Okay, here, this is a side view. You've got a load, and again, you can see that that cable is going to make this drum spin, which causes the axis to spin, which causes the motor to spin. And there, that is where the drum and the motor are joined together. That is a clutch. Okay, clutch allows you to join your driving force device to your machinery that you need to make go round, and so on. Yeah, that. Oh, okay. Look, 3 diagrams to show how the moment of inertia of this diver changes on his way down. Okay, and oh look, they've given you a graph of how the moment of inertia changes. okay, it's really complicated. This is how you get caught out. So you do need to practice doing questions, because you've got to be able to interpret all that information. Okay, all the information in the diagrams and the descriptions and how things are changing. Oh, that's a Catherine wheel. Okay, so fireworks making things spin. Oh, it's exciting. Okay, so just so that you're aware that that's probably the hardest bit of the engineering physics option topic. Okay, so we've now got a torque, and it causes an angular acceleration of the moment of inertia of whatever it is that's attached. Okay. Can you see it says you will not be asked to derive the torque equation at all, but you are going to have to apply it in familiar but also unfamiliar contexts. In other words, they might give you something weird. I mean, there was one year where there was an object that was spun around on the end of a string. And it was used in a military situation in a forest for military units to keep communicating with each other without using radio. And you spin this round and it makes a whistling noise. Oh my goodness, it was angular speed and resonant frequencies and goodness knows what. Yeah, unfamiliar contexts might very well come up. The more practice papers you do, the better it will be. Okay, so it says it's important to stress the use of appropriate units. Okay, so kilogram meters squared is the unit for I. Kilogram meters squared. So remember that I is the sum of the mass times r squared. So that's where the kilograms meters squared comes from. Okay, so and rads, so this is okay, sorry, that so because the torque is I times alpha, and the unit for I is that, and the unit for alpha, remember that alpha is the angular acceleration, so it's delta, delta omega divided by delta t. Ooh, get a cup of coffee, thank you very much. That then is, this is the angle, so it's the second derivative, delta, it's this, I don't want to do second derivatives, I'm going, but of course omega is the rate of change of angle, so this is, can you see, it's rads per second squared, that's the equivalent units for this, which means that the torque, can you see, is this one, kilograms meters squared, and then this one, rads, seconds to the minus 2. That is effectively the unit for the torque, but you shouldn't use that. You should, because torque is it's Newton meters. Right, now I'm going to remind you, so you shouldn't use that, you should use that. I'm going to remind you that work is also force times distance, right? But when it's work, the force and the distance are parallel to each other, okay? And I suppose I ought to use S, shouldn't I? F times S. Okay, so that indicates that it's a vector, and you have the cos theta if they're not in parallel. Okay, so that's work. Now, torque is also force times distance, but here this is not work. You can't use joules because the newtons and the meters are at 90 degrees to each other, and you don't get joules unless they are in line with one another. So Newton meters is the correct unit for torque, and joules is the correct unit for work. Okay, so this is work. Work done. Okay, so so you need to be aware that although the equations look like they're the same, because the force and the distance or displacement are at 90 degrees to each other, no work is done. Okay. Okay. Yeah. Right. Let us clear all of those. So there is the thing about units. So Newton meters is the correct unit for torque. In linear motion, we would not expect a student to write the unit of force as kilogram meters per second squared. So yeah, it should be newtons for force. Okay, so in linear motion, the F in F equals ma is the unbalanced or resultant force. The same applies using the torque. So it's the unbalanced torque. It's the resultant torque. So if you've got two moments acting in opposite directions, then it's one minus the other. That gives you the resultant torque that then causes the acceleration. So all of the stuff about resultant forces that you remember with your linear motion, you have to apply here to torques for your angular motion. Okay, so there are usually, there's a frictional torque which acts at the bearings and it opposes any applied torque usually. And this causes losses of energy in rotating engines, and so it causes complications. When we get onto the heat engines bit, you get complications of loss of power at every stage in the powertrain for a car, for example. So you need to be aware that there are different definitions of power. So there's the power of the fuel that's going in, and then there's the power at the crank, and there's the power at the wheels, and they are different, and you need to learn those definitions, but we're not going to do that right now. So you need to be aware that there is friction in most rotary systems that opposes motion, and it is the resultant torque that you need to use for T is I alpha. Okay, it can be found experimentally, and this is quite important. So they might describe doing this, and you have to work out what the friction force is from the description. So it can be found experimentally by taking the wheel or shaft or object up to speed, removing the accelerating torque and allowing it to gradually run down to a standstill. So you can measure the friction. Okay. If the deceleration and moment of inertia are known, then the average decelerating or frictional torque can be calculated. And so that's one of the questions that they might ask you to do. Okay, that's that one. And then we come on to angular momentum. So angular momentum is I omega. So you've got linear momentum, which is mv, and the equivalent to m is I, and the equivalent to v is omega. So this is angular momentum, and this is linear momentum. And remember, for linear momentum, momentum is conserved. And so mv, I suppose it's the sum of mv before is equal to the sum of mv after the collision or whatever it is that's happening. And that's the same for angular momentum. So angular momentum is conserved. So the sum of I omega before is equal to the sum of I omega after. And if you've just got one object or two objects being attached together, for example, then you only, it's a bit like you know, a car crashing into a lorry. You've got two objects, so you have to allow for the momentum of both of them, and they just add. Okay, it's the sum. This, I hope you're aware that this means the sum. Okay, this is a Greek letter, capital letter sigma. Okay, so if we read what it says that the student should know that the angular momentum is I omega, and that the units for angular momentum, remember that it's, I suppose, yeah. So you end up with Newton meters seconds. It's a bit like, remember that this equation, that Ft is equal to delta mv. So your momentum in linear momentum, we usually do kilogram meters per second, don't we? But it's also the same as Newton seconds. Can you see those units are entirely equivalent to each other? So linear momentum, we nearly always call kilogram meters per second, but you can call it Newton seconds. Well, we've got the same thing over here. This is torque times time, and that gives us our change in angular momentum. So we've got Newton meters seconds there, and that is equivalent to I, which remember was kilograms meters squared, because it's I is mr squared, or the sum of it. And then the angular speed is the angle, rads, per second. So that is the equivalent, but we don't use this one. We do use this one, but we don't use this one. So we use Newton meter seconds. This is angular momentum unit. I hope you can read that on your screen. So it's Newton meter second, which is why we use the Newton meter second. So it's the equivalent to Newton's statement of his second law, where impulse is equal, right? Impulse, oh dear. Impulse is equal to change in momentum. And we have the equivalent here. This is angular impulse. And that is equal to change in angular momentum. Okay, so entirely equivalent. Can you see how the links between them mean that if you understand the linear stuff, the angular stuff just falls out? It's great. So there is the units for angular momentum. Okay, so you should understand that the angular momentum is only conserved in cases where no external torque acts. So don't write where no external force acts. We're using the word torque instead. Okay, so conservation of angular momentum occurs when there's no external torque acting. And then conservation of angular momentum can be demonstrated by sitting a student on a swivel chair, preferably one not fitted with casters, asking the student to hold kilogram mass in each hand, and then get them to fling their arms out. So that's got quite a large moment of inertia, and then when she puts her arms in, she speeds up. Okay, so the angular speed. So that's conservation of angular momentum. It's rather nice, isn't it? So that's a large moment of inertia. That's slightly smaller, so she's going a little bit quicker. Don't worry about that equation. They've called it L. It's not, it's I on your specification. And then when she brings her arm and her leg in, the moment of inertia I has got smaller, and so the spin has to get faster. Okay, so they've mixed up the moment of inertia and the angular momentum in this description. So don't watch that video, but just look at the way that the ice skater changes. Yeah, I decreases because R is getting smaller when she brings her arms in, so omega has to increase, so she spins faster. Okay, right, where were we? Okay, so this is angular momentum, and oh yeah, that so illustrates why divers tuck themselves in when they spin. So should we have let's go and have a little look at so he brings his arms and legs in so that he can spin fast enough that he can get round twice before landing. Okay, so and you can see he was practicing doing it without a swimming pool. Okay, so that diver thing where they bring their arms and legs in order to spin quickly means that they can then when they extend their body again, the rate of rotation slows, so they can time it so that they are in the orientation they want to be in when they actually land. So yeah, that means that they can do it. So trampolinists, dancers do it as well. Ice skaters brings their arms in, and so on. Okay. And then there's simple clutches, and this is where you get the sum of the angular momentums before and the sum of the angular momentums afterwards. Can you see this is where you've got two masses? So imagine linear momentum, and you've got train trucks and they lock together so that afterwards they're moving together. Well, this is the same thing. So you have to add the two equivalent masses, that's the equivalent moments of inertia, moments of inertia, and you multiply it by the common angular speed because they are now locked together. So you've got one thing spinning, the other thing was stationary, and it goes, and now they're locked together and they're both spinning with the same angular speed. So so you just need, and drawing a picture of before and afterwards nearly always helps. The angular momentum before, the angular momentum after. Okay, and angular impulse is force. Well, it's not, it's torque times time. Okay, it's the same thing as linear impulse, but it's torque instead of force, still time. And then work and power are exactly the same, except the work is torque times the angle instead of the force times the distance, and power is the torque times the angular speed instead of the force times the linear speed. So and all of that is exactly the same as the linear stuff. And then we've got back to the analogy. So this is what I wanted to cover in today's session. We're going to go on to thermodynamics engines, heat engines, and so on next time. Okay. I hope that you've enjoyed that, and I will see you all soon.